All right, so we're going to take a look at example 2 in the curve sketching notes. So again, we're going to write down everything we know about this function, basically from pre-calculus. It's an odd degree with a positive lead coefficient. So we know that f is continuous. We know that it's differentiable. We know that the domain is negative infinity to infinity and that there are no corners, no cusps, and no vertical tangents. So all we have to worry about is our critical values when the derivative is equal to 0. That would be the only candidates for extrema. We know that the limit as x goes to negative infinity of f of x will be negative infinity, and the limit as x goes to positive infinity of f of x, our end behavior is going to be infinity, that positive lead coefficient, odd degree, so they're opposite directions and it's in an increasing fashion. We know that there is at least one x-intercept and up to 5 x-intercepts. We don't know. It doesn't factor nicely, so I'm not going to worry about that to come up with our x-intercepts. And I also know that this is neither even nor odd. If I plug negative x in, this term would be opposite, that term would be opposite, and this one is, of course, going to be plus 3 because there's nothing to plug in there. So that would be the same, which means it's a mix of even and odd. So it's neither even or odd. So we have no symmetry on this one as well. So then we start our calculus, which is we're going to take our derivative. So f prime of x is going to be 15x to the 4th minus 15x squared, which does factor very nicely. Take out your 15x squared, and we have x squared minus 1. So our critical values, f prime of x equals 0, or x equal to plus or minus 1 and 0. We can create our sign chart, putting our critical values on, negative 1, 0, and 1, f prime, so 0, 0, 0. F prime is an even degree with a positive lead coefficient, so it's positive on the ends. Plus and minus 1 are single multiplicity, but x squared is going to be double multiplicity, so it should switch here, stay the same, switch there. So what that tells me about my function f is increasing, decreasing, decreasing, increasing. And I also know that f has a local max at x equal to negative 1 because f prime switched plus to minus. F has a local min at x equal to 1 because f prime switched minus to plus. All right, so I know that when I go to graph this, I'm going to have to find f of negative 1, and I'm going to have to find f of 1. And, plugging that in, that's something that should be fairly straightforward for you guys. So I'm just going to tell you what it is. F of negative 1 ends up being 5, and f of 1 ends up being 1. So we'll have those coordinates, right, because it does say here that they want us to find the coordinates of the relative maxes and mins. So I have done that now. I know that we have coordinates of negative 1, 5 for the max, and we have coordinates of 1, 1 for the min. So we've satisfied the coordinates of the relative extrema. So then we'll come into and we'll do our second derivative, f double prime of x would be 60x cubed minus 30x, which you can factor out of 30x, and that's going to leave me with 2x squared minus 1. So f double prime of x equals 0 for x equal to 0 and x equal to plus or minus the square root of 1/2. And if you would like to, you can do plus or minus square root of 2 over 2. It doesn't really matter in terms of the values that you have for that. You can leave it here, you can leave it there. You could have left it as plus or minus 1 over root 2. We don't really care. Remember, you don't have to simplify, so any of those would have been fine. Let's create our sign chart. So come down here. Now, square root of 2, 1 over square root of 2 or square root of 2 over 2, approximately where they are. They're not as 1 over square root of 2 is going to be a fraction, so it's somewhere in here. So negative 1 over square root of 2, 0, 1 over square root of 2. Just kind of lining them up because when I do this, it makes it easier when I start sketching. There's our second derivative. It's a cubic with a positive lead coefficient. So we have our increasing fashion, so it should be down, it should be up. We have 3 roots and they're all single multiplicity, so it switches each time, so it should be plus, minus, plus. All right, what that tells me at each of these critical values is that, or possible points of inflection, is that f has points of inflection at all 3, and our f switches concavity at each of these values. So we're concave down, concave up, concave down, concave up, and f has points of inflection at x equal to plus or minus 1 over square root of 2 and 0 because your second derivative switched signs. Right? And they ask for the coordinates. So again, you would have to come and plug in f of 0, f of 1 over square root of 2, and f of negative 1 over square root of 2. And just using your calculator and plugging it in. For negative 1 over square root of 2, you get approximately 4.2. Now on the AP, of course, we do 3 decimals, but for what we're doing here, this one is 1.76, and f of 0 is 3. So our coordinates would be 0, 3, 1 over square root of 2, and approximately 1.76, and negative 1 over square root of 2, and approximately 4.2. So we get our coordinates of that. And so at this point, you're ready to go ahead and do your sketch. I'm going to do that on a separate page. Let me pause for just a second. So what I've done is I've taken those 5 points that we had. Here's our relative max, there's our relative min, and then the 3 points of inflection. So I just plotted them on the graph. And so we basically just have to connect the dots following the behavior of f. So before this relative max, we know that f has to be increasing and concave down. So you pretty much, like, hey, it has to be increasing and concave down, increasing, concave down. And then it would be decreasing all the way to the relative min, which is over here, but it has to change concavity at each of these places. So we would be down, and then up, and then down, and then up. And then we have our min, and then we have to increase from there. So you pretty much get the shape of your graph by connecting the dots and following the behavior. And then if you wanted to check out, this is what I got, just basically sketching it, and then what it actually looks like if I look at it on the calculator is this right here. So you can see that we've got the correct shape, increasing, concave down, then switches concavity, switches concavity, switches concavity, and then concave up. So we get our picture that's there.